PCR, or polymerase chain reaction, uses repeated cycles of denaturation, annealing, and extension to exponentially amplify target sequences. A typical PCR reaction mix includes the following key components: a template that contains the target sequence, the forward and reverse primers, a polymerase enzyme with a preferred reaction buffer, and finally, dNTPs and optional additives to help boost your PCR. All of these components will not work together properly without the individual denaturation, annealing, and extension steps that make up thermocycling. The composition and length of the template play a critical role in deciding the type of DNA polymerase and cycling conditions to be used. Templates can be GC-rich, AT-rich, or longer than normal. These factors affect primer design considerations, as well as whether the polymerase has sufficient endurance for the reaction. Having a good pair of primers is instrumental to a good PCR outcome. General parameters to consider when designing primers include primer length, the balance between GC and AT-rich domains without any complementary sequences, and the primer annealing temperature. Different DNA polymerases are best with different conditions and different buffers. Be sure to choose a thermostable DNA polymerase along with an appropriate buffer that meets your PCR application needs. The final concentration of dNTPs, nucleotides, the building blocks for new DNA strands, in the PCR reaction determines PCR yield. Optional additives such as betaine, DMSO, and BSA can be added to boost PCR efficiency. Don't forget to consider these. For optimal cycling conditions, carefully consider the number of cycles, as well as temperature and duration for individual initialization, denaturation, annealing, and extension steps. Troubleshooting a PCR reaction involves many factors. Selecting the right components and cycling conditions for your needs can help achieve optimum results. For more details on PCR products and protocols, explore sigmaaldrich.com/PCR.